All right, today we're going to talk a bit about enzymes, but we can't talk about enzymes without talking about chemical reactions. So a chemical reaction is a reaction where bonds, remember bonds are electrons, are rearranged. So if we take this classic reaction, so this is photosynthesis. So we have 6 waters, so the 6 here is a coefficient. So a coefficient multiplies. So if it's a big number in front of a chemical compound, then multiplies. So it has 6 waters. Now the other number here is called a subscript. All right, so the subscript, that little blue number there, just multiplies the atom in front of it. So if I have 6 waters and I have 2 that multiplies hydrogen, I have 12 hydrogens. Okay, so those are those type of things. This little purple arrow here is the yield, right? So yield in a math equation is kind of like an equal sign, right? 6 plus 6 is equal to 12, right? So the yield is an equal. So we could say that all these things on the left-hand side are reactants, and all the things on the right-hand side are products, just like it says here. So we can say that reactants yield products. All right. So let me erase some of that stuff here. I'll get back to it. Oops. And that little mark over here. There you go. All right. So if I look at this reaction, 6 waters and 6 carbon dioxides yield C6H12O6, otherwise known as glucose and oxygen. All right. So that's our basic photosynthesis reaction. I don't know what happened there, but okay. That's our basic photosynthesis reaction. So remember I told you that a chemical reaction is one where bonds are rearranged. So if we look at this right here, right, so my hydrogens here become my hydrogens there. My oxygens here actually become my oxygens there, right, because a splitting of water creates oxygen in photosynthesis. My carbons come here, and this oxygen over here ends up there. So what I've done is I've taken my reactants and I've rearranged them, and I put them in my products. Now that can't happen without enzymes, right? So it can't happen. One thing that you have to know is these must obey the laws of conservation of mass, matter, and energy. So you may remember this, that mass, which is the same as matter, right? So that's the law of conservation of mass and matter. Same for energy. Energy can't be created, destroyed, only transferred or changed from one form to another, but I can't get rid of it or create it. So what this says is if we looked at it and we counted it as 12 hydrogens in the reactants, if I came over, I have 12 in the products. If I have 6 carbons in the reactants, I have 6 in the products. And if I have 18 oxygens, I come over here and I still have 18 oxygens. Okay. All right. There. Okay, so we'll come down here. So enzymes and regulations. Now we're ready to talk about enzymes. So enzymes. We'll talk about that first. Enzymes are catalysts. Catalyst is the chemistry word. In biology, we call catalyst enzymes. right? So they speed up reactions by lowering the activation energy. So this E sub A right here means energy of activation or activation energy. It's kind of like if I have a pile of wood at the beach and I want to have a bonfire. It just doesn't start burning. I've got to put energy to it in order to start the reaction. Once I start it, it'll continue to burn until it's done, right? So the activation energy, right, so we can find that right here. I need my pen to work again. There we go. So my activation energy I can find here and there, right? So without a catalyst, right, my activation energy is large. So this is what we refer to as the activation barrier. So that's the activation barrier. So that's the amount of energy I have to put into it to get it to start. What a catalyst does is it lowers this activation barrier, right? So the reactions are more favorable to continue. And that's one of the main purposes of enzymes in your body, is to make the reactions so they're favorable to go. So this is what's called an exergonic reaction. Just go here. An exergonic, so it's energy releasing. So this is the energy of my products. This is the energy of my reactants. I mean, my reactants are over here on the left-hand side, and my products are over here. Right, so this exergonic are energy releasing, so it released right? So the opposite of exergonic is endergonic. So if we have exergonics, so endergonic would be energy absorbing. So we talk about metabolism a little later. We'll say that exergonic reactions are tied to endergonic. So if you're releasing energy in one reaction in your body, you're absorbing it in another reaction in your body. Right? So it's important to know that the catalyst in this is not used up in the reaction. Right? But exergonic here, products have less energy than reactants. This is an important part right here, so put a star next to that. So enzymes are not used in the reaction. So after the reaction is done, the enzymes are released, and they can come find more reactants to make products out of it. Okay? All right. So biological enzymes. Let's talk a little bit about biological enzymes. Kind of work here. All right. So biological enzymes. So biological enzymes, right, what they say are specific for a substrate. So the substrate is the biological way we say reactant. Right? So in chemistry, a reactant is like a chemical you find on the periodic table or a molecule you've made. In biology, substrates are biological molecules like carbohydrates, nucleic acids, proteins, right? So they're specific. So specific here means only so we don't have one enzyme that does a bunch of stuff. Each enzyme we have is specific or only works on one type of substrate. Okay? So substrates bind. So they bind to the enzyme's active site, which is usually groove or fold. So this right here would be the active site. This right here would be the substrate. And this would be the enzyme. Alright, so the enzyme has an active site, and then it fits its substrate. And they say it fits like a lock and key, right? So they say it fits like a lock and key. So we talked about conformation, remember. So the conformation or the 3D shape of the enzyme must be an exact fit like a lock and key. Remember that 3D shape is our tertiary conformation. So primary is our string of amino acids, right? Secondary are my alpha helices and my beta pleats, right? And the tertiary is my three-dimensional structure of it. So mechanisms of enzyme interaction. So here's the difference. So a catalyst in chemistry may speed up the reaction by increasing the amount of collisions, right? But in biology, the enzymes, the way they work, right? I can't heat up your body to make things work faster because your body's temperature stays kind of constant. Remember, that was called homeostasis. So in biology, what the enzyme does is it orientates the substrate, right? So it fits in the groove, and it holds it so it can either put it together or take it apart, right? So it puts it together and take it apart. So it orients molecules. That's the way it does, right? So that their active sites are in the correct position, right? So these molecules could bounce against each other many, many, many times. And eventually a reaction will happen, but it will not happen in the time you need it to happen. So the enzymes hold them in place so that the reaction is favorable. Right? So once bound, it may change the bonds a little. It may flex some. I can't get my pen to work again. There we go. Right? It may stretch or weaken or bend bonds. It may create an environment that makes things come apart. Right? So then they make brief bonds. So if I have my enzyme right here, this is my activated complex, right? Complex. And then what it's doing, it's weakening these bonds here, causing the product to fall apart. So it's important to know that enzymes usually. All right. So enzymes can't always be turned on, because if they were always turned on, you would start to run out of substrates in order to make products with, right? Or enzymes that take things apart, right? We would have everything taken apart and there'd be nothing left to work with. So enzymes need to be turned on and off. So there's a couple things. So an activator turns on an enzyme. And an inhibitor, so an inhibitor and an activator. An inhibitor turns off an enzyme, right? And they do this it's accomplished by changing or blocking the active site. Okay, so remember the active site is the active groove. So in this picture right here, I have the active site right here. Right, so I have a substrate which blocks an active site, right? Or that's a regular substrate, right? And then it forms the product. So in here, right, I have an inhibitor, and it changes the shape of the active site. So this molecule right here wouldn't be able to fit in there. Okay, so that's an inhibitor, an allosteric inhibitor. So we have allosteric inhibition and activation. So we have competitive and non-competitive. So a competitive inhibitor will block the active site. So here we go. This is a competitive inhibitor right here. And you see it's something that is close enough to the substrate where it weakly binds to the active site. And it makes it so the substrate can't fit. This is what we do with a lot of medicines, right? So a lot of our inhibitors that we use to help with brain function, right? So that inhibitor, right, that medicine we give the patient will block this active site so the biological molecule can't bind to it and can cause something to happen, right? A non-competitive inhibitor binds to what's called an allosteric site somewhere else. So allosteric means not to place, so it binds to another place and it changes the conformation. And if it changes the conformation of the active site, then the substrate won't fit. So that's competitive versus non-competitive. So this would be non-competitive right here. So a lot of your body, though, in biological processes works by what they call non-competitive or negative feedback. So in negative feedback, in a negative feedback loop and intermediate, an intermediate or something created in the process or product right? So an intermediate or something that's made in the pathway or a product, they act as an inhibitor, right? So if we have this pathway right here, so I have a substrate that binds to an active site, right? So I have an intermediate substrate here, right? So if this activates my next enzyme, I have another intermediate substrate, it activates my enzyme 3, and then this product then goes and changes the active site of the enzyme so it can't make the process happen again. Because remember, the enzyme's free to work again. Right, so a good example of this is when you have blood sugar, right? When you eat food, you start to produce insulin in your pancreas, right? So the glucose activates that, but an intermediate in that pathway will then turn off the production of insulin. So that way you only make some insulin, right? But you don't make so much you run out of blood sugar because insulin will shove sugar in your cells. So that's called a negative feedback loop. So make sure you know that a negative feedback loop right here, right? An intermediate or product acts as an inhibitor. Okay, that's it for now, and I'll talk to you soon.